solubility product constant. Turns out when an ionic compound dissolves, it's an equilibrium process. And so we can calculate an equilibrium constant, but instead of calling it KEQ, we call it KSP, solubility product constant. So that's the equilibrium expression for the dissolving of an ionic compound. Remember that we do not include concentrations of solids in an equilibrium expression. If this equilibrium constant, the KSP, is very large, it means the products are favored. The dissolved substance is favored, the solubility is high. If KSP is small, it means the products are favored. The amount of ions present is going to be low. It's not very soluble. So we can treat these very much like the problems we did earlier today. So what we're going to do is we'll first write the chemical reaction. They won't necessarily give you the chemical reaction. They'll just say, calculate the KSP for barium sulfate. Well, then you need to write this equation. So barium sulfate as a solid is in equilibrium with the ions that are present in it. So this has one barium ion and one sulfate ion, and so we see Ba2 plus and SO4 2 minus. Then you write the equilibrium expression based on this chemical equation. So it's products over reactants, but the reactant here is always going to be a solid. So there's not going to be a denominator. It's the barium concentration times the sulfate ion concentration. So KSP is used as a measure of the solubility of a compound, and you can look up KSPs for all kinds of compounds. There's a small selection given in your textbook, and especially in mastering chemistry, you might have to refer to this to solve a problem that's given. Now, you do not memorize these things. Nobody memorizes those. So if you need one on an exam, I'll give it to you. Okay? So looking at this table, we can see that some of these things, like lead sulfide, the solubility is very, very small, 10 to the minus 29. And some of the others, it's larger, like 10 to the minus 6, magnesium carbonate. That's still not super soluble. So we talked earlier about the rules, the solubility rules, right? And we said, okay, well, these things are soluble, these things are insoluble. It turns out nothing is perfectly insoluble. Practically insoluble, yes. But all of these are in equilibrium with their ions. And so we learned that silver chloride is insoluble, right? Well, there's an equilibrium constant for silver chloride. It's 1.77 times 10 to the minus 10. But in a solution, there will be a few silver ions and a few chloride ions. But they'll be so small, the concentration will be so small that it's probably not going to matter at all. So write equilibrium expressions for each ionic compound. So KSP, this is solubility product. So the first thing we have to do is write an equation for how this dissolves. So silver iodide, that's a solid. And what two ions is it going to form? Silver ion, and that's going to be aqueous, and iodide ion. There's that whole nomenclature thing coming back. So KSP, products over reactants, but the reactant is a solid. So we've got silver ion concentration times the iodide ion concentration. And that's the expression. Any questions? Let's do this one. Calcium hydroxide. So that's a solid. And what ions does it form? Calcium ion, that's got a 2 plus charge. Aqueous plus hydroxide. You can only break this up into two ions. Okay, you can't have hydrogen and oxygen separate. It's only two ions. And so that's aqueous. But is this balanced? No. So down here we have a subscript 2. That means that we're going to have 2 hydroxide ions. And so then the equilibrium expression, KSP, is going to be the calcium ion concentration times the hydroxide ion concentration squared. Okay? So this needs to be balanced in order to get the correct KSP expression. Oh, that's a good place to stop.